Cool. All right, so Lewis structure for methane. We put our carbon in the middle, kind of decorate it with all the different substituent atoms, and then we draw those lines connecting those two. Importantly, each one of these lines represents 2 electrons that are being shared. All right, so how many total electrons do I have on this board right now? Let's everybody put it in the chat for me. How many electrons do you think I have drawn in my Lewis structure for methane? Cool, right? We all get it, seem to get it pretty well. So each one of these represents 2. I have 2, 4, 6, 8. So I have 8 electrons on the board for my Lewis structure of methane. Methane is going to be the simplest organic compound that we could possibly be talking about here. So we're only going to get more complicated from here. So let's make sure we understand these structures, and then we'll go on. And so that's kind of how you were taught to draw these Lewis structures for, you would be given a compound formula like this, and then you would look at the periodic table. Let's bust out our periodic table. And you would count the total number of valence electrons for each of your atoms. So let's make sure we know how to do that. Get rid of all this business. Okay. And actually the number of valence electrons in a particular element corresponds to what row they're in, right? So everything over here in this first row has 1 valence electron in it. Everything in this second row has 2 valence electrons in it. And then we're going to skip those transition metals because they're kind of a pain in the butt. So we're just going to hop right over that. Everything in this column have 3 valence electrons. Carbon has 4 valence electrons. Nitrogen has 5. Oxygen 6. The halogen 7. And then our noble gases have 8, right? So what column you correspond, what column the element falls in corresponds to how many valence electrons are in those atoms. Valence electrons are those what we call the outermost electrons. Really, we care about them because they're what dictates the chemistry of an atom. Turns out that all atoms with, for example, 4 valence electrons behave very similarly. Carbon and silicon have very similar bonding patterns, right? So everything that falls within a row here has really similar chemistry, which is why the periodic table is arranged the way it is. And that corresponds to the number of valence electrons in those atoms. Okay, all sounding familiar? Cool. So we can tell the number of valence electrons depending on what column it is. So in this particular example, we had CH4. So we would look on our periodic table for carbon, and we would look on our periodic table for hydrogen. Carbon has 4 valence electrons. Hydrogen has 1, and there are 4 such hydrogens. That's how we get to a total of 8 valence electrons for this compound. Everybody take a second and make sure that you can see why methane has 8 valence electrons. Okay, again, carbon has 4, hydrogen just has 1, but I have 4 hydrogens in this compound. All right, so when we were drawing our Lewis structures, the name of the game was figure out how many valence electrons a compound has total. And then when you go to actually start, drawing it, you need to make sure that you have that same number of electrons down on the board. So we had 8 total when we drew our collective Lewis structure for methane. Okay. So that process works, don't get me wrong, but because this is organic chemistry and because we're going to be talking about so few elements, there's actually an even easier way, an even easier set of rules that I'm going to teach you that will have you always drawing correct Lewis structures. Okay. Let me get my whole thing. Okay. All right. And the rules are as simple as certain elements like to have a certain number of bonds. And since we're restricted to so few elements, it's just easier to learn this tiny set of rules. So let's start with carbon. Carbon. Actually, let's arrange it like this. Okay, again, carbon is going to be the star of the course, right? Every single organic molecule contains carbon. Carbon likes to have 4 covalent bonds. So if you're drawing a Lewis structure and you got carbon in there, you just need to make sure that all carbon atoms have 4 bonds, and you'll know that your Lewis structure is correct. Okay, and likewise, carbon has no lone pairs. Just to remind everybody what lone pairs are. If we had, for example, the Lewis structure of water, we would have oxygen bound to 2 hydrogens, and then on that oxygen would be 2 lone pairs of electrons. So these are electrons that are sitting on this atom, but they're not participating in any bonding. That's what we mean by a lone pair of electrons. Remember, the bond consists of shared electrons. The lone pair is electrons that are sitting on that atom, but they're not shared. Okay. Hydrogen. Also going to be seen over and over and over again. Can only have 1 bond. So for just about every element on the periodic table, we say we want to fill the octet of that element. We want to give it 8 electrons. Hydrogen is so teeny tiny that it can only have 2 electrons that are associated with it, right? It's that first element on the periodic table, just 1 proton. So hydrogen's a little bit of an exception in how many electrons will be associated with it. Only ever going to have 1 bond or 2 electrons associated with a given hydrogen atom. And 0 lone pairs. Oxygen. How many bonds we think oxygen likes to have? Everybody show me what they think. All in their hands. Let's look at water here. How many bonds does oxygen have? 2. Oxygen likes to have 2 bonds and 2 lone pairs. All right, so if you're drawing a molecule in organic chemistry, you want to make sure that that oxygen has 2 bonds associated with it and 2 lone pairs on it. Okay, and then the last one is nitrogen, which likes to have 3 bonds and 1 lone pair. Okay, so we had this sort of 5-step procedure for drawing Lewis structures in Chem 3A or 1A, where we totaled up the number of valence electrons, and then we made sure to organize them such that they were all drawn on the board here. You can do that, that works, but it becomes incredibly cumbersome for large molecules. If we stick to this simple set of rules here, we will get a correct Lewis structure in organic chemistry. Okay, and the nice thing is that then when we get to bigger and uglier molecules, this simple set of rules still works. All right, so let's go one more complicated than methane, which would be what we call ethane C2h6. All right, we're gonna get even more complicated as we go here, but let me just show you how sort of to approach these. If our goal is to draw the Lewis structure for these organic molecules. First of all, I'm going to note that hydrogen can only have 1 bond, right? So there's no situation where I'll have something like this. That's automatically wrong because my hydrogen has too many bonds there. So first of all, just the general strategy is you're going to put all your carbons down first, And then you're going to decorate it with the hydrogens at the end. The hydrogens are going to be the easy ones because, again, they only have one bond associated with them. They're not going to be like in the middle of two other atoms. Okay, so the first thing I'm going to do is just put down my 2 carbons. Okay, and then I'm going to continue making sure that each carbon has how many bonds. Everybody show me, how many bonds are we looking for? 4, right? Our carbon should always have 4 bonds. So 1 more, that would bring me to a total of 2 for this carbon, 3, 4, and then I'm done, right? If I go something like this, this should make everybody's chemistry brain explode. Carbon should never have 5 bonds. It's just not going to be a thing, right? So as soon as it has 4 bonds, I know I'm done and I can move on to the next one. So again, this carbon over here has just 1 bond. So 2, 3, 4. Right? So by following these simple rules from above, I can make sure that I have a correct Lewis structure just by giving each element the correct number of bonds. Okay. Let's do another one. So now we're going to do ethanol, which is like drinking alcohol. The one that gets you drunk is actually the organic molecule ethanol. That has the formula C2H6OH. You could write this C2H6O. That's perfectly okay as well. I'm going to show you why we write it like this here in a second. Okay, but everybody, I'm going to give you 2 minutes. Take a stab on your own using our simple rules for drawing organic molecules. See if you can't give me the Lewis structure for ethanol here, C2H5OH. All right, so again, my general strategy is going to be to just ignore the hydrogens at first. My goal is to get everything else down, and then I'll decorate it with those hydrogens at the end. So I'm going to put my 2 carbons. Now I have this oxygen in there as well. Oxygen doesn't just have 1 bond, it has 2 bonds, so it's not as easy as hydrogen. So we're going to make sure that's down as well. And now we can go through and decorate it with these hydrogens. How many hydrogens should I add to this green carbon here? Nice, yeah, 3, right? To make sure that it has 4 bonds total. So 1, 2, 3. All right, and let me see everybody's hands. How many hydrogens should I add to this red carbon here? It just needs 2 of them, right? Because it's already got 2 bonds. So in order to satisfy this one's octet 1, 2. And so then that last one will be on that oxygen. Okay. The other thing I'm going to need to make sure is that, again, all elements aside from hydrogen want a full octet, right? Meaning they want 8 electrons associated with it. If I look at this oxygen right now, it has 4 electrons associated with it. So it needs 4 more to make it 8 total. Those other 4 electrons are going to be those lone pairs, right? Oxygen likes to have 2 bonds and 2 lone pairs. All right. Everybody, I want you to convince yourself that this carbon right here has 8 electrons associated with it. Point to them on your paper. All right, so 2, 4, 6, 8. So that carbon's happy. And then do the same thing with this oxygen here. Convince yourself that there are indeed 8 electrons associated with that oxygen. Two, 4, 6, 8. Right? Each lone pair has 2 electrons, and each bond has 8 electrons. 8 electrons. Each bond has 2 electrons. Okay. So when I did the when I did the molecular formula for ethanol, and you'll notice how instead of doing like this most condensed version, C2H6O, I actually wrote it as C2H5OH. And that was to show that I have this OH group in there. Okay. Either one would be technically correct, but you're going to see over and over and over again when we write these molecular formulas in organic chemistry, they kind of give you a hint as to what functional group is in that particular molecule. Okay, don't worry about doing that correctly yet. We'll worry about writing molecular formulas and all that good stuff. Right now, we are focused on connecting these atoms correctly, building these Lewis structures. The names, methane, ethanol, we don't know that crap yet. I'm going to be using them so that they sort of sound familiar to your ear when we get to it, but we're going to go through this whole naming process. We're not there yet. Again, our entire goal for today are these Lewis structures, just connecting these atoms correctly. Okay, if the other parts seem a little fuzzy, that's cool. That's because we haven't gotten there yet. All right, very much so my style of teaching revolves around teaching you guys skills, and I like to focus in on a particular skill. I always say the class is going to be hard enough without me trying to be tricky. I don't have to be tricky. I can tell you exactly what I expect you to know, and it's going to be its own thing, right? I could pick a bajillion of these organic molecules to have you draw structures on. So there's going to be a lot of variety out there. The whole point is, do you know how to draw an organic structure correctly? That's our skill that we're learning today. Okay. Cool. So, and just to note, there would have been one other molecule that you could have drawn. It wouldn't have had this OH functional group in there, but it would have had the same molecular formula. And that is if I had put that oxygen in the very middle, I could have then gone through and decorated with my hydrogens. Given the lone pairs to oxygen. This doesn't have this OH, what we call functional group in there, but it's a perfectly legal Lewis structure. This molecule absolutely exists in organic chemistry as well. So it's not like for every molecular formula, there's a unique molecule that you can draw. In organic chemistry, that's kind of what makes organic chemistry a little bit tough, is the arrangements of the atoms. You can sort of switch stuff around. Okay, both of these, take a second and convince yourself that both of these follow all of my rules for drawing structures in organic chemistry. I didn't break any rules, didn't do anything illegal here. So both of these are perfectly correct structures in organic chemistry. I have a carbon with 4 bonds, both of my carbons rather with 4 bonds. All of my hydrogens only have 1 bond. My oxygen has 2 bonds and 2 lone pairs, right? All that checks out. Okay. All right. So now we're going to take a second. You guys are going to give me a structure that has the formula C4H10. The bigger we get, the more of a pain in the butt it can be, right? But that's what as long as we follow those simple rules, we'll be good. Okay, one other thing that I kind of meant to point out, and I just want to be clear. If focusing on this structure, some people, some people get focused on how these atoms are drawn in space, like their orientation. I have like carbon, oxygen, hydrogen all in a line. If instead I had moved my hydrogen over here and my lone pair over here, that's perfectly cool too. Okay, the sort of like the spatial orientation of how you draw these lines doesn't matter for these types of structures. All right, so just be clear, those are two equivalent things. Those aren't two different structures. They're the exact same thing. What these structures really tell you is who's bonded to who and where those electrons lie. That's really the pieces of information that we can get from these structures. All right, so now going to our new example here. Again, my strategy is going to be to put down the carbons first, right? I'm going to deal with the hydrogens after the fact. So I'm going to put down my carbons. 1, 2, 3, 4. If I give you one of these problems, the easiest structure, we're going to see that there's actually a few structures that have that same C4H10 structure. The easiest one to do is all the carbons in a line. Okay. And then we can go through and decorate with those hydrogens. Again, we're going to make sure that all of our carbons have 4 bonds. So that means this one needs 3 hydrogens. When I get to this second one, it already has 2 bonds. So it only needs 2 hydrogens. Same with the third one. And then the last one, I need 3. Cool. We all got that? Let me see. Thumbs up, thumbs down. Who got it right? Cool. So when all the carbons are in a line like that, we call that the straight chain. Okay. But there's a different molecule that I can write that has this exact same formula, but has a different connectivity of those atoms. I want everybody to take a stab at it. See if you can't draw me a different molecule than the one we just drew here. Has that same structural formula, C4H10, but the connectivity of those atoms are different. All right, if you think you got it, hold it up to your camera here. Let me see. All right, so we're going to have the same molecular formula here. So 4 carbons, 10 hydrogens. That's not going to change. The difference is going to be, again, that connectivity of atoms. So what the heck do I mean by that? Meaning that who's bonded to who is going to change here. But we're still going to have to follow those same simple rules that we followed before, where carbon has 4 bonds and hydrogen has 1 bond. And since hydrogen only has 1 bond, again, the easiest thing to do is to wait and add those at the end. They're never going to be like in the middle. So really the name of the game is to take that carbon, what we call the backbone of the molecule, the carbon backbone, and rearrange those carbon atoms. And so what I would mean by that is instead of having each carbon atom just bound to 1 or 2 other ones, for this here, we have this middle carbon that's actually bound to 3 other carbon atoms. Okay, notice that I just took that carbon backbone. This one was this. And I just rearranged it by moving a carbon atom. right? This was the backbone of my straight chain molecule, all carbon atoms just sitting in a row. And now this is the carbon backbone of what we call a branched. So if this one was straight chain, this is a branched chain. Somebody got a question? You can just yell it out.
Oh, okay. Quick question. What if I have the same branch chain, but the carbon is on the top side?
Same exact thing.
Okay.
So the sort of where these are arranged on the page doesn't really matter. It's all about who's bonded to who. So this is the exact same thing as this. Okay, so and this is going to be a subtle point, and we're going to talk about things called stereoisomers. It's one of the hardest parts of organic chemistry is being able to look at a molecule and see if it's the same as another molecule that's written, but in a slightly different way. This is just something that we're going to get good at over time. Okay. Like I said, this course is all about structure. We're going to be looking at structures over and over and over again in this course. Okay. You'll get better at it as we go. So anyway, in this branch chain here now, I'm going to go through and draw in my hydrogens. Again, following those same simple rules. Notice that now this middle carbon isn't going to have 2 hydrogens associated with it because it already has 3 bonds. So how many hydrogens am I going to add to this carbon here? Just 1. And then this bottom one here needs 3. Okay, so I want you to convince yourself that this structure here has this same molecular formula. Go through and count the carbons, count the hydrogens. I want you to convince yourself that we followed those same rules that we were talking about before, where carbon has 4 bonds and hydrogen just has 1 bond. All right, the difference again is our carbon backbone. This is this straight chain, and this one is the branched chain. All right, since these 2 molecules share this same molecular formula, we call these structural isomers. All right, that's going to be an important vocab word from today, structural isomers. They have the same molecular formula, but a different connectivity of atoms.
Quick question.
Yeah.
Are they the same molecules or are they different molecules?
They are different molecules. They'll have slightly different properties. They have the same molecular weights because they have the same number of carbons and the same number of hydrogens, but they'll have like different boiling points, stuff like that. So they will behave differently.
Okay. All right. Thank you.
Yep. Good question. All right. So this is an hour-long class. You can go by quick. I'm going to leave you guys to give me 2 structural isomers of this formula that I'm going to put down. And while you're doing that, I'm going to take attendance. So we're going to do just give me 2, and there are many more than 2. So if you're feeling, spunky, you can go ahead and draw more than 2, but give me at least 2 structural isomers that have the formula C5H12. All right, so first of all, the easiest one to get of our 5 carbon molecule here is going to be the straight chain, right? So I'm just going to line them all up, 1, 2, 3, 4, 5. And then I can put my hydrogens around it. So this would be kind of the easiest structural isomer to draw, that straight chain. Okay. And then again, there's sort of multiple branch chain molecules that you can draw here. There are many structural isomers that have this same formula, but the idea is you're going to take, let's say we have our straight chain here, and you're going to move one of these carbons. So I'm going to take this one on the end and move it over here, for example. Okay, and then you're just going to go in and fill in, remember about the rules of how many hydrogens there are, right? So each one, you can just make sure to complete each carbon's octet with these hydrogens. So 1, 2, 3. This one needs 2. That one only needs 1. Okay, another one could have been if we had something like this, where this middle carbon now has 4 other carbons bound to it. If I go through and decorate this with hydrogens, I indeed get the same molecular formula. So this would have been another structural isomer that you could have drawn. Again, the most important thing is that I'm following those simple set of rules where carbon has 4 bonds, hydrogen has 1 bond. If we have oxygen, it has 2 bonds and 2 lone pairs. And if we have nitrogen, it has 3 bonds and 1 lone pair. Okay, so that was our goal for today, was just to be correctly drawing our Lewis structures. Again, because this is organic chemistry and we're focused on so few molecules, or rather so few elements, we can sort of dumb down our Lewis structure rules to this simpler set that we talked about. Okay, importantly also, we learned this new term, structural isomer, which is, again, 2 different molecules that have the same molecular formula, but a different connectivity of atoms. Those are structural isomers. All right, so we're going to be done. I actually have a class right after this as well, so we're going to have to make sure to finish right on time here. If you guys have any questions, you guys are more than welcome to stay and make sure that I get it. Okay, so Amanda K is here. You can definitely have more than one branch. That's perfectly okay. Like in the second or the third structural isomer I drew, had those 2 carbons coming off of that middle carbons. All right, but so I'm done with you today. Again, you'll look out for those that homework assignment, which will be posted by tomorrow. Again, usually I'll be good and have it done beforehand, so you can work on it right after lecture. Today, I'm still getting our OWL system figured out, but it's going to revolve all around these Lewis structures, being able to draw these molecules correctly. Okay, so again, I'm done with you. If you guys want to stay around and ask any questions, you feel free to do so.